Hello students, Jai Swaminarayan. I am Professor Urvish Mewada, HOD Electrical Department, Sri Swaminarayan Institute of Technology, Bhat, Gandhinagar. I am the subject matter of Power System 2 subject, which is in the 5th semester Electrical Engineering, and GTU subject code of this subject is 3150911. Students, today we are starting with the fresh new chapter, chapter number 5, Symmetrical Components. Students, in last lecture we have finished the chapter number 4, Symmetrical Fault Analysis, in which we have discussed the example based on the symmetrical fault analysis. Now today we are going to discuss the new chapter, that is symmetrical components. So let us discuss the components of the symmetrical power system. Now in this is the lecture number 1, in which we are going to discuss the topic number 1, that is introduction of symmetrical components. So let us discuss how this components can be described. So basically, whenever we have a large power system, so it is also called a complex power system. So basically a power system are large and complex in three phase. So in normal operating condition, the electrical power system operate in balance condition. So what do you mean by balance condition? Means all the three phases are drawing same voltage and current, and there is no any harmful flow of the fault current or the heavy voltages. So it is called the balance condition, and hence it can be represented as the equivalent single phase system. Now in the and however there are certain situations, say whenever the fault or any short circuit arises, that can cause the system to become unstable. So this is the reason to become system unstable. Instead the system remains in the balance condition whenever it is in the healthy condition, but whenever such kind of fault occur like a short circuit, then the system can become unstable, and the single equivalent system method of analysis cannot be applied to the such unbalanced system. So for that unbalancing, we need to apply certain methods to determine or to check the condition of that fault. So there are two methods available for such analysis. The first method that we use is Kirchhoff's law, and the second method is symmetrical component method. So these two methods can be applicable to determine such unbalanced or unstable condition of the power system whenever the fault arises. Now in these two methods, the Kirchhoff's law is very difficult to analyze for the analysis of the unbalanced system, because it that will become very like very complex for the Kirchhoff's means to solve using Kirchhoff's law. It will become very complex to solve the system. So the symmetrical component method is very much suitable to determine the parameters of this unbalanced system using symmetrical component method. And symmetrical component method was developed by CL Phoscuse in 1918, and it is a powerful technique for analyzing the unbalanced three-phase system. Now as we have discussed that whenever there is no any contingency occur, means contingency of, say, if when the system is at healthy state, means all the three phases are means transferring same amount of current, or we can say the load which is connected to the system is balanced. So that at that time that system is called balance. And whenever any kind of fault occur in the power system, there are so many types of faults arise day to day in the power system. So if any type of fault occur at that time, the current through any of the phases will change, or it will increase or decrease. So it is called a fault, or any type of short circuit occur, then the system will become unstable. And due to due to this reason, the all the phases will have a different amount of voltages and current. So we need to check that all the parameters of the power system at the time of fault. So the Kirchhoff's law and the symmetrical component method both are the methods that we can apply to solve such unbalanced system. So let us discuss the symmetrical component method, which is most suitable to determine this unbalanced system. Now, the Phoscuse theorem, this is the most MP theory of this chapter. So let us discuss what Phoscuse theorem states. So in this Phoscuse theorem, the symmetrical components method for the Phoscuse theorem, basically it is in 1918 the CL Phoscue introduced the concept of the symmetrical component, and the theorem which states that if of the n unbalanced, means we are having a large power system and it is interconnected, so we are having a n unbalancing whenever any such fault occurs. So n unbalanced set of the phasors which can be resolved into the set of n minus 1 balanced phasor. So the systems balanced phasor system of the different phase sequence plus 1 0 phase sequence system. So this system ultimately means divide this analysis in, say, three part. So we have, according to the means according to the Phoscuse theorem, we have three unbalanced phasor voltage, means phasors in which we have voltage or currents, and of three phase system of power, which is called say we have three parts, that is positive sequence, then negative sequence, and zero sequence phasor. So Phoscue basically divide this unbalanced system in three part for the analysis of the unbalanced and unbalanced, means set of the phasor, and which are divided in three part, that is called positive sequence phasor, negative sequence phasor, and the zero sequence phasor. Now positive, negative, and the zero sequence component of the original unbalanced phasor of the three phase system are called the symmetrical component. So we are converting this all three phases from the original unbalanced phasor. So these components are nothing but the symmetrical components of the unbalanced system, we for which we are finding the solution. Now here we are considering the three phase unbalanced voltage, which is means which having a voltage which is designated as VA, VB, and VC. So we are having three phases, so that's why voltage of A phase, voltage of B phase, and voltage of C phase. So according to the Phoscuse theorem, this phase voltage can be resolved in the three state. So let us discuss that all three states to determine the symmetrical component of the original unbalanced phasor for the three phase system. So first is the positive sequence component. So in the positive sequence component, we are considering the three phases which are equal in magnitude, so and which are displaced 120 degree to each other and having the same phase sequence in original phasor. So if we consider A, B, C, then this is the sequence of this three phase system. So it will be VA1, VB1, and VC1. The figures related to this the symmetrical components is shown next in the next slide. So please go through it carefully, and means try to understand this positive sequence, negative sequence, and zero sequence. Now this is called the positive sequence. Now what about the negative sequence? So negative sequence in here consisting the three phase which are equal in magnitude, displaced from each other by 120, but and having opposite phase sequence of that original phasor. So when in the positive sequence we have considered VA1, VB1, and VC1. So the opposite phase sequence means it will be the VA1 will become VA2, VB1 will become VB2, and VC1 will become VC2. So this is called the negative sequence of the system. Now the what about the zero sequence? So zero sequence, and we are consisting the three phases which are equal in magnitude but with a zero phase displacement. So in the case of positive and negative sequence, we have all the phases are 120-degree apart to each other, but in the zero sequence component there are phases which are having zero phase displacement and from each other, and which are designed as VA0, VB0 and VC0. So let us see in this diagram. So this is the three unbalanced phasors. So there is no means uh, equal phase distribution between each other. This is VC, this is VA, and this is VB, and this is the reference line. So there is no equal angle distribution between each other. So first is the positive sequence of this component, three unbalanced phasor system. So this is the reference on which we have taken VA1. After VA1 means 120-degree to VA1, we have the VC1, and then 120-degree we have the VB1. So VA1, VC1 and VB1. Now if we consider the negative sequence, then VC1 will change its position and means 120-degree to each other. So this VB1 will be over here and VC1 will change over here. So this is the interchanging of the phases. So VB1 will become VB2 and VC1 will become VC2, and VA1 will become VA2. So this is the negative sequence. So the addition of this positive sequence and the negative sequence and the zero sequence phases is the three phase unbalanced phasor, and this is described with the help of Phoscuse theorem, and from that Phoscuse theorem we can easily determine all the parameter of this unbalanced system. Now we can write the equation for the VA, VB and VC. For VA we have the voltage VA for the, since we have each of the original unbalanced phasor is the sum of its components. So the original phasor which expressed in terms of their components, so these are the components of this original phasors. So VA, the component of the VA is VA1 plus VB1, VA2 plus VA0. So over here the this is the VB, the VB1, VB2 and the VB0, and then it is VC is equal to VC1, VC2 plus VC0, where VA1 plus VB1 plus VC1 are the positive sequence component from this. This is the first part that we have taken from this VA1, VB and VC1. It is called the positive sequence component, and VA2, VB2 and VC2, this is the negative sequence component, and VA0, VB0 and VC0 is the zero sequence component. So this is how we can bifurcate all the components of three unbalanced phasor, and from which we can determine the parameters related to the unbalanced power system to solve the fault level of this three phase complex system. Now over here you can see that this is the original phasor in which we are changing the phases, means sequence of the phases. So as we change the phase sequences, the positive, zero and the negative sequence phases are changing to the each other, and this is the value of the phasor, which is means magnitude of the phasor that is changing over here. So after changing this any of the phases, the positive sequence, zero sequence and negative sequence phases will change, and the original phasor will be the addition of this all three positive sequence, negative sequence and zero sequence component of the given power system. So from this animation that will be more clear to you that whenever we change any of the phases, according to the change in the phases, the positive sequence, zero sequence and negative sequence phases will change, and its magnitude will also change. So all three will remain same, means in the each of the cases, but the placement of the phases will change in terms of positive sequence, in terms of negative sequence. and you can see the magnitude of all the phasor values. So please go through it very carefully, and that will be more clear to you. This is the second animation of this positive sequence, negative sequence, and zero sequence. So in this positive sequence, you can see that when the if you consider a blue, means this is the means color of the phases, red, yellow, and blue. So you can check the position whenever the red is at over here in this. So then this is 120 degree apart to each other. So all the phases are not, means if we superimpose this to diagram, then this phases will remains 120 degree apart to each other, and the phase sequence will also change in terms of positive sequence as well as the negative sequence. In negative sequence, you can see that red is red, and then yellow and blue both are interchanged. Instead of yellow, there we have the blue, and blue instead of blue we have the yellow phase. So this is describe the position of the positive sequence and the negative sequence of this component. And this is the zero sequence, in which all three phases are rotating, having equal magnitude, and this is the vector sum of this all three quantities. And this describes that the equivalent of or we can say total of the symmetrical magnitude of the total magnitude of the equivalent symmetrical component of the power system. So this is how we can discuss the symmetrical component of the power system. Now let us discuss the topic number 3. So topic number 3 is a complex operator, and which is indicated as alpha. So let us check the what is the role of complex operator alpha. So in this case, so let us discuss the complex operator alpha. Now before we discuss the complex operator alpha, we are here discussing this diagram. In this we have the phase A. So A is displaced with the angle theta, so in the direction, say anti-clockwise direction, and after A dash, A we have the A dash, and then after 120 degree to A dash we have the A double dash, and means 120 minus theta degree we have the A double dash, and after A double dash means we have 240 minus theta degree we have the A triple dash. So this is the position of the phasors, and let us discuss how this operator means play its role in the solution of the complex power system for the symmetrical components. So let vector OA, which is shown in this figure, and when it is displaced by means angle theta, and then anti-clockwise direction, it is can be expressed that OA dash is equal to OA, and we have the angle that is cos theta plus j sin theta. So that's why we can write for this cos theta plus OA, we can means we can write for cos theta plus j sin theta for the exponential term, that is OA into e raised to j theta, where OA is the reference vector. And if the angle displacement is 120 degree, so this theta will become OA into OA into e raised to j 120 degree, and which occupies the new position that is called OA double dash. And if the e raised to j 120 also represented by the alpha, then it will be OA double dash is equal to OA into alpha. Now this alpha can be alpha may be defined as the unit phasor which is oriented an angle of 120 degree with reference to the unit phasor. So the alpha can be written in terms of the polar r angle theta form, so that is 1 at angle 120, and alpha has magnitude of say unity, and angle is 120. So just like a operator, j is equal to 1 at angle 90, so it rotates means rotates a phasor forward through plus 90 degree and anti-clockwise direction. So we can also say that the multiplication of the vector by the complex operator alpha will rotate the vector by 120 degree in the clockwise anti-clockwise direction. So this is indicates that the rotation of the vector of for the for the certain angle. And it is over here it is shown that 120 degree of the rotation of the say means vector in the anti-clockwise direction. Now in say some important properties of the alpha operator which is shown over here. So over here you can see that this is alpha 2, and this is alpha 3 from after the reference line. So yes, we can determine the value of all the operators, means all the position of the vector. So alpha is equal to e raised to j 120, so it is 1 at angle 120, and we can write that in terms of cos theta plus j sin theta. So theta is 120 over here, so cos 120 plus j sin 120. And for alpha raised to 2, the angle will become 120, means addition of the phase from 120 to 120, so displacement, so it will be 240. So e raised to j 240 is equal to say 1 at angle 240, or we can say we can write the 1 at angle minus 120 because it is an anti-clockwise rotation of the phasor. So cos 240 plus j sin 240 will be minus 0.5 minus j 0.866, and for alpha raised to 3 it will be an addition of 120 more to alpha raised to 2, so it will be j 360. So 1 at angle 360, so it will be 1, so alpha raised to 3 is equal to 1. And for alpha raised to 4, the means we can go further, then that will be alpha raised to 3 into alpha. So alpha raised to 3 is equal to 1, so alpha raised to 4 is equal to alpha, and alpha minus alpha square is equal to j into root 3, and alpha square minus alpha is equal to minus j root 3. So above is the relation for alpha from 1 to 6 are very important and very useful for the simplifying the results obtained with the symmetrical components of the phasor. So over here 1 at angle minus 120 degree, which is conjugate, is 1 at angle 120. So when we take the conjugate, we'll remove the sign of the operator. So these are the relation which describes the components of the unbalanced phasor. So this is how we can solve the operator alpha. Now let us discuss the topic number 4 for unit number 5 is synthesis of unsymmetrical phasor from their symmetrical components. So let us how we can bifurcate all the sequences. So synthesis of this symmetrical components. So this technique is used to analyze the unsymmetrical fault, and in unsymmetrical component technique, the three unbalanced voltages that we have already discussed, that in power system we have three phases, and whenever the system is at healthy condition, means there is no any fault occur at that time, the system remains stable, and if any kind of fault occurs, say short circuit or any like load and balancing is there, then all three phases means will grab the different amount of voltage and current, so that is called the unbalancing. And this unbalanced voltage or current are converted into the three set balance that we have already discussed, three set balance voltage or current, which are known as the symmetrical component. And the symmetrical components are divided in three parts. The first part is positive sequence, second is negative sequence, and third is the zero sequence component. So this is again a most MP question of this theory. So let us discuss the positive sequence component. So it is in this diagram you can see that this is the positive sequence, VA1, then VC1 and VB1, that we already discussed in the first theory. And over here the positive sequence component is a set of the symmetrical voltage. So over here these are the symmetrical voltages which are equal in the magnitude, and and have the 120 degree phase difference to each other. So we have already defined the operator. So initial operator was alpha, so from VA1 to VC1 we have the alpha displacement, so it is called 120, and then we have the alpha raised to 2, and then we have the alpha raised to 3. So this is the separation of the all these phasors. Whenever we are solving such kind of components, or say positive sequence components, so this due to this phase sequence, they are known as the positive sequence component, and this this phase sequence is given by A, B, C, and it is denoted by VA1, VB1, and VC1. So VB1 will be the alpha square into VA1, and the VC1 will become alpha into VA1. So when we multiply it with the operator, so that gives the value of the next consequent phasor. So mode of VA1 is equal to mode of VB1 is equal to mode of VC1. So all are the all are means will all will become equal. So this is how we can explain the positive sequence. Now let us discuss the negative sequence. So in negative sequence we have changed that the placement of the phasor. So in the negative sequence all the magnitudes of this phasors will remain same, but the means and the magnitude have 120 phase displacement, and it is negative phase sequence are known as the negative sequence component. So we have just the interchange the placement of any of the phase. So they have the in the case of positive sequence we have the ABC, in this case we have the ACB. So the also they are denoted by the VA2, VB2, and VC2. So this is called the negative sequence of this unbalanced system, and this is the separation of the phases. So you can see that from the VC2 to VB2 we have the alpha separation, then VC2 to VA2 we have the alpha square separation. This is the operator complex operator of the power system. So VB2 is equal to alpha VA2, and VC2 is equal to alpha square VA2. So VA2 is equal to VB2 is equal to VC2. So that's why VA2 plus VB2 plus VC2 is equal to 0. So this is the negative sequence component of the unbalanced system. Now let us discuss the zero sequence component. So in the case of zero sequence component, a zero means a zero sequence set of the three voltages which are equal in magnitude and have the same phases are known as the zero sequence component, which is shown in this diagram A. So VA0 is equal to VB0 is equal to VC0. The separation means there is no phase difference between each other. So that's why VA0 plus VB0 plus VC0 is equal to 3 VA0. So all are equal. So the addition of the sequence component we can describe by this way. Over here you can see that the zero sequence component, positive sequence, as well as the negative sequence component, and this addition of the sequence component. So over here you can see that this is the VA0, this is the VB0, and this is the VC0. All are having same direction, and there is no phase displacement between these three. So this describes the zero sequence component of the this unbalanced system. And then after we have the VA1, VB1, and VC1. This is the VA1, this is the VC1, and this is the VB1. So this is called the negative sequence component. And then we have the VA, then VB, and this is the VC. So this is the basic means addition means this is the means initial state of the unbalanced system. And then we have the VA2, then VB2, and then VC2 is the positive sequence of this unsymmetrical means component of the this system. So this is how we can do the addition of the sequence component, and this is how we can explain all the sequences of this system. So after this you have the worksheet question. These are the the question is for the worksheet. So explain Phoscuse theorem for the symmetrical component, also explain the complex operator with suitable derivation, and explain the synthesis of the unsymmetrical phasors from their symmetrical components with suitable phasor diagram. So the after that you have the the instructions related to this question. Please read it carefully. Also you can take the snap of this slide, and if you have any doubt or query after this topic, then we can solve your doubts and queries in our doubt solving session. If you have any further queries arise, then you feel free to call me anytime to solve your doubts related to this topic. So thank you very much, student. Thank you all. Jai Swaminarayan.